Hello everyone. Today I'll be talking to you about some fundamental neural mechanisms that are required to understand how neurons and neural circuits function. So all neurons possess the potential for electrical activation, and this is governed by the existence of a electrical charge relative inside the cell relative to the extracellular space. This is governed by the cell membrane, which is a semi-permeable layer, allowing ions to cross the membrane only when their specific ion channel allows it. And so we can see here that there are ion concentrations inside and outside the cell. And so, for instance, sodium ions, shown here as Na plus particles, and chloride ions, shown as Cl minus particles, are in high concentrations in the extracellular space, and potassium ions, shown as K plus particles, are in high concentrations in the intracellular space. And so when their specific ion channel is activated, for instance, this pink one here, being a potassium ion channel, when it becomes activated, it opens a pore which allows potassium ions to travel down the concentration gradient, in this case into the extracellular space, to essentially try to establish an equilibrium across the membrane. And so one other thing that this simultaneously does is to create an electrical gradient. There are more positive ions outside the cell, which makes it relatively more positive than the intracellular space. And so this negative intracellular space is what's referred to as a resting membrane potential. So let's get to what happens when this resting potential changes. So very small changes, which are called initiations, but that do not reach threshold, do nothing to the cell. It returns to its resting state. Every cell has a set threshold, and once a charge inside the cell changes enough to reach this threshold, it triggers what we call an action potential. And so when an action potential occurs, we get this rapid depolarization. And this is governed by the opening of sodium channels. And you'll remember that sodium is in a high concentration in the extracellular space. So the opening of these channels allows an influx of sodium ions down the concentration gradient, and that makes the intracellular space more positive. This continues for a very short amount of time, and then we see these sodium channels inactivate, and we see potassium channels opening. These channels were both triggered at the same time. However, the potassium channels are slower to open, and so they don't occur until this action potential peak is reached, and this triggers what is called a repolarization. And this is the cell potential inside the cell becoming more negative. This occurs because potassium ions, which you'll remember are in a high concentration inside the cell, are flowing out. So the internal environment becomes relatively more negative. This continues beyond the resting state of the cell and becomes much more negative than it normally is. And this is called a refractory period. And during this refractory period is when we see potassium channels closing and sodium channels remain closed, but after a prolonged period in the refractory period, they regain the ability to activate again and fire another action potential. So action potentials cannot occur during this refractory period due to the time required for sodium channels to reactivate. But after this refractory period, we see a return to a resting potential. And so one other characteristic of an action potential is its dynamic. It moves along an axon, and it moves in one direction only. Here we have a schematic of an unmyelinated axon shown at the top and a myelinated axon shown at the bottom. And these myelinated axons simply have a sheath of myelin that wraps around the cells, and the ion channels I mentioned earlier are pushed into these areas between the sheaths, and this area is called the nodes of Ranvier. And so what I want you to think about now and see if you can come up with is why an action potential moves along an axon. So think about what happens when an action potential triggers. We see an influx of positive ions. So I want you to try to think about what would happen to the ions that are already in the cell when it suddenly becomes more positive. I'll give you a second or two to think about that and see if you can come up with a reason. Okay, so hopefully some of you thought about, hopefully all of you thought about the fact that when these positive ions, these positive sodium ions flow into the cell, there is already positive potassium ions present in the cell. And so what happens when a positive ion meets a positive ion, or a positive charge meets a positive charge? They repel each other. And so what we would see is when the sodium ions enter the cell, the potassium ions that are already in the cell are repelled along the axon. And they are repelled in both directions, but they're repelled along to a neighboring space, which makes that space more positive, and triggers an action potential there. And so we see this stepping along the axon. And this occurs in the same way in unmyelinated and myelinated axons. However, of note is that because you've got lots of channels together in a myelinated axon, you get much greater influx, so the repulsion is much greater, and the positive potassium ions jump much further, and they'll jump to the next node of Ranvier and trigger an action potential there. And this tells you why the myelinated axons conduct a signal much faster than the unmyelinated, because it's essentially jumping longer periods along the axon. And so the reason it can only travel in one direction is that, for instance, after this region of the axon had fired an action potential which had spread along the axon to this next area and triggered an action potential, this area would actually repel axons in both directions, would repel ions in both directions. However, you'll remember that after an action potential there is a prolonged refractory period. And so this region of the axon is in its refractory period, and so essentially the only way that the charge can be passed on is in one direction. And so that brings us to what happens at the axon terminal. So the charge travels down the axon to the terminal. At that point, instead of having a sodium influx, we see calcium ion influx, which binds synaptic vesicles and leads to the exocytosis of neurotransmitters into synaptic cleft, and these neurotransmitters bind to receptors on the postsynaptic cell and essentially activate a postsynaptic cell and allow it to fire its own action potentials. And so this is just a little table that summarizes some of the major neurotransmitters in the brain, and for now, through this module, we'll mainly be going through glutamate and GABA. And there is, so glutamate is implicated in learning and memory and neuroplasticity. And while we're on that subject, there is a required reading that is posted to the module page, where there is an article by Soderling and Derkach that summarizes the role of glutamate and its receptors in neuroplasticity. And so Also listed here are several other major neurotransmitters and their functional role in the brain. And throughout the semester, we'll be going over these in much more detail. So I look forward to going through that with you soon. Thank you.